Hey, if we can turn to the worksheet that we were working on yesterday at the end of class. Let me just recap how we were pulling the width, the height, drawing the subintervals, and then I'm going to have us work on this back page. And I just want to walk around and make sure that you guys feel comfortable getting all that information. So let's do a recap of that first, going over number one. So the big idea with all these problems, for most of these, it's just area of a rectangle. So just width times height. As soon as you see a table of values, you're never going to use this b minus a over n. Okay, you're only going to use this if there's nothing given to you except the function, the a, b, and the n value. Then we can build our width. But here, table of values, we're going to pull the width from the table. We're not going to create our own. Okay. Okay, so the next thing that we do is make sure that we understand that we are starting and ending with the appropriate interval, right? Not every problem is going to span the entirety of the order pairs that you see. So for part A, it says create middle rectangles with 3 subintervals. The first thing you want to do is just create your 3 subintervals. Okay. Every subinterval that you draw, make sure that you start at the middle of your first order pair, and you're going to extend to the middle of the order pair that ends your subinterval. So here, first subinterval, I'm going to span across 3 order pairs. The second subinterval, I'm going to pick up where I left off. Each subinterval is going to start where the previous one ended off. So you're always going to have a shared order pair when you build your second interval. Second interval will start at 8, we'll go to 12. Third interval from 12 to 20. Notice that every subinterval sees exactly 3 order pairs. Doesn't mean the width is the same, but we've created the subinterval width that we need. Okay, and now next we want to find the width. When you find the width, make sure that you're not adding the 2 numbers together, right? You want to find the distance between these 2 values. So it's 8 minus 0, which is 8. 12 minus 8 is 4. 20 minus 12 is 8. That's how you find the width. Now the height is going to come from the second row. Make sure that you're not pulling values from the top row anymore. That is not going to be involved. You're just going to pull the height from the bottom row. It says middle rectangles. So the 4 would be the height of the left rectangle. The 3 would be the height of the right rectangle. But the middle rectangle is going to be the 2. So maybe some of you guys are thinking, wait, 2 is not quite the midpoint because 5 doesn't land between 0. It's not, 4 is the true midpoint. Now, when it says middle approximation, you're just using whatever the table gives you, right? It could be all the way over at 7. It could be all the way down at 1. Middle just means between, okay? You want to find the y value that sits between the left and the right. 8 times 2 is the area for the first rectangle. 4 times 7 is the area of the second rectangle. 8 times 6 is the area of the third rectangle. Okay. Total them together, and that'll get you your area. Okay. Okay, if you look on the board here, area of a trapezoid is width over 2 times height 1 plus height 2. We want to make sure that we can apply that as well for that 4th problem we're going to see on the back page. Okay. And when you do trapezoid, make sure that every trapezoid area formula that you're only pulling height 1 and height 2. You may be tempted to want to use every y value that you see, but the formula only calls for 2 heights. So for part D on the first page, width is 9, but the height is just 4 and 7. You're only using the ones at the ends. Okay. And also, we're not going to double the heights that we saw from the previous problems, right? Because those are where we build from scratch, and also those are maybe ones that have multiple areas where there's like 6 or 8. If there's that many trapezoids, then we like to kind of double up the heights, and especially the widths are the same. But here the widths are not the same. We're forced to add the areas of trapezoids separately. Okay. All right, so if you guys can turn to the back page, I want you guys to try those problems starting with 2A. I'm going to walk around and just see how you guys do. And that way I can confirm whether you're good to go or if you need some more additional support to help with creating the information needed to get that approximation. Okay.
Okay.
Numbers are close. So trapezoid, there's the intervals. I'm starting at 3. Tomorrow you will, sorry, Friday you will get to use a calculator. Okay, bring a calculator for the quiz.
Got some track. 4 minus 1. Starting at 3. So 3. I don't need to get that spot.
Okay, most of your work looks pretty good. Let me just go through the answers here. So A should be 43. B should be 89. Careful that that you're paying attention to your interval, right? You're not always starting at 1 and you're not always ending at 20. So we're starting at 3, so you got to build your subinterval starting at 3. Okay.
Will the tables always be 1 through 20?
No, it just depends on whatever the table I give you, right? Third subinterval, part C, you should get 51. Make sure that for your heights that you're looking at the second row, that you're not accidentally pulling the height from the first row, right? The first row is just for the width. The height is going to purely come from the second row. And then part D, 83. Okay. Just want to make sure that you guys feel really comfortable with these types of problems because it'll show up on the quiz or show up on the test. These are the most popular ways of AP exam testing your Riemann sum knowledge. They like to go through using table of values. So if you're comfortable with it, then when you see it on the AP exam multiple times, you'll be able to know what to do, how to pull information about using certain rectangles that they specify for you. Yes.
Can you do C, but like just like the first rectangle?
So part C, it says use left-handed rectangles with 4 subintervals from 1 to 12. So all we're just paying attention from the interval from 1 to 12. We want to create 4 subintervals. So 1 to 3 will be the first subinterval, 3 to 7, 7 to 10, and then 10 to 12. Okay. And then within each subinterval, you can subtract the x values. So 3 minus 1 gives you 2. So the first rectangle is 2. Second rectangle is a width of 4. Third rectangle has a width of 3. Fourth rectangle is a width of 4. Sorry, width of 2. Okay. It says left-handed rectangles. So that means for each subinterval, you're going to pick the left height. So first subinterval left height is 3. So 2 times 3 is the area of the first rectangle. 4 times 6 is the second rectangle. 3 times 1 is the third rectangle. And then 2 times 9, last rectangle. Good. All right, any other questions with table of values, Riemann sums? Okay, let's go to page 11 in your packet, 4.1 packet, and we're going to start going through one of the quiz reviews. Okay, does everyone have a 4.1 packet? I got some extra. Okay, so it says find the sum. We're not gonna use summation formula because it's only a few terms. We're just gonna add them one by one. So we're gonna start with 2 because that's the lower bound. So insert 2 in for I, and then total that value up. Summation means we're gonna add a bunch of terms together. So the next term is plus, what's the next I value? 3. And then we plug that in, get that value, and then next is 4. We stop at 4 because the upper bound says 4. That means 4 is the last I value that you enter into the expression. Okay. All right. So try that. See if you can insert. You can use your calculator. Yes, add parentheses and then square. Good. We'll do order of operations.
No. Wait, what? Oh, right, yeah.
Okay, any questions with number 1? Okay, let's look at number 2. So number 2, what we're doing here is we're working backwards here. We're given something that is representing the sum, but we want to put it back into sigma notation. So we basically want this to happen. We want to be able to enter I equals 1 into an expression to get this, or into a formula to get this expression, or this representation. We need to be able to plug 2 in for I into some expression to get this value. And then I equals 3 into some expression to get this value, and I equals 4 to get that last value. Okay, so let's just build it piece by piece here. And now I'm going to start at 1. I'm going to end at 4. So it may seem a little intimidating, right? How do we know where to begin? I would say let's do the easy parts first. Okay. The easy parts are the parts that keeps repeating itself, that are unchanging. So whatever is unchanging, I know it's going to keep showing up, so I'm just going to copy that down. So the division sign is unchanging, the cube root is unchanging, the 5 minus is unchanging. So I'm just going to put all the pieces in place, and then I can worry about the parts that's going to involve I. Okay, we know that the 2, 4, 6, 8 is going to involve I because it's going to keep changing, and because it's going to because of the I value changing is causing these values to change. So can we create a rule that will allow that to happen? What can I plug I into an expression to get 2, 2 in to get 4, 3 to get 6, and 4 to get 8? To I, okay? And whatever you create, you want to go ahead and just check it, right? It's going to be a little bit of guess and check, trial and error. You can get a rule to create what you want to create. So if I plug 1 in for I, 2 times 1 is 2, that's good. If I plug, next up is 2, 2 goes in for I, 2 times 2 is 4, 3, 6, 4 times 2 is 8. Okay. What's going to go in this space? Also 2I, right? It's the same pattern. Okay. Any questions? Okay.
Can we go to the first one?
Yeah. Good. Okay. All right, let's look at number 3 here. Number 3 says use 3 middle rectangles to approximate the area bounded by the function, the x-axis, x equals 1 and x equals 6. Now here, they don't give you, there's no table of values. There's no indication as to the width. So this is where we build the width on our own. Okay, this is where we have to involve b minus a over n. Okay. If there's no indication as to what the width is, then you use the b minus a over n. But if you see a table of values, you're not going to use this, right? The practice on that last worksheet, you guys know how to find the width, the intervals, the heights, okay? But here, it's just basically a blank slate. We have to create the width on our own. Okay, so your A is 1, your B is 6, and your N is what? 3. 3 is the number of intervals here. Okay, so A is 1, B is 6, N is 3. Okay, let's find our width. B minus A over N. Okay, so that means we created, right? We're gonna, every subinterval rectangle is gonna have a width, same width as 5/3. Okay. Now we have to build our subintervals now. Okay. So starting with the left endpoint, which is 1. You're gonna keep adding the width until you reach your next subinterval x value, and then you're going to keep going until you eventually hit 6. Okay, so 1 plus 5/3, same thing as 3 over 3 plus 5 over 3, which is 8/3. Okay, 8/3 plus 5/3. I'm just keep adding the width to my previous subinterval. I get 13/3. Add by the subinterval again, 13 over 3 plus 5/3 is 18/3, and that's exactly 6, right? All right. Now, if it was just asking about left rectangle or right rectangle, we can just rely on these values, right? Because every subinterval, we have left and right endpoint. But it's asking for middle rectangles. So middle rectangles means we have to find the midpoint to attach to the graph. So we have to find the average of these two numbers to find that midpoint. Okay. So the way we find average of two numbers, we add the two numbers and divide it by what? 2, right? Which is the same thing as saying adding the two numbers and multiplying by 1/2, if you just don't want to think about it as dividing by a number. So imagine we're just going to add the two values and getting that middle point there. So 3/3 plus 8/3 is 11/3. Multiply that by 1/2, and we get 11 over 6. So 11 over 6 is the midpoint of the first interval. Yes. I'm sorry?
Like, can you not say, like, divide 5 over 3 by 2?
You mean 11 over 3 by 2? Because we're trying to find the average of two numbers, so I've got to add them together before I divide by 2. Were you subtracting?
The original, like, that's gotta be 5, 6, and then you just add that.
That's fine. That works too.
Oh, okay, yeah.
Yeah, you can find the half of the width and then just keep adding 5, 6 to every term to get that subinterval. That's fine as well. Okay, you can also use your calculator to do the work for you. 8/3 plus 13/3 is 21/3. Take the two values, divide it by 2. Same thing as multiply by 1/2. So 21/3 times 1/2 is 21/6. Okay. 13/3 plus 18/3 is 31/3. Divided by 2. Same thing as multiply by 1/2. 31/6. Okay, you don't have to know what the graph looks like. I just want to kind of give you some perspective here. So this is a parabola. The parabola is going to rise to the right, something like this. And essentially, right, this is not the way that we draw these rectangles is not going to give us an exact area. It will just give us an approximation. So imagine just taking these midpoints, we're attaching them to the curve, and then we're using that to dictate the height of each rectangle. All right, so 21/6 is going to attach to the curve. We're going to get that height. 31/6 attached to the curve. We're going to get that height. So we're just going to basically find the width and height of each of these rectangles and then just add them together, and that'll be our approximation. Okay, we know the width of every rectangle is 5/3. We know the height of the first rectangle is going to come from 11/6, but it's not just going to be 11/6, right? It's 11/6 into the function. So I'm just going to represent that as f of 11/6. I haven't found the value yet, but at least I know how to move on to my next step, right? I'll insert 11/6 into the function, and whatever decimal value I get will be the height of that rectangle. Okay, second rectangle, every width is 5/3. Width times height. The height of the second rectangle is f of 21/6. Third rectangle is also width of 5/3. And then we're going to attach 31/6 to the curve to find that location, f of 31/6. Okay, any questions about the process so far? Finding the width, finding the subinterval, finding the midpoint, and then moving to area. Okay, using your calculator, you can enter 11/6 in for x, 11/6 squared plus 3, get a decimal value, and then just do the calculation portion of it using your calculator. Yep.
So,
Or it's that part, yeah, yeah.
So that's gonna enter into the x.
You're like half close.
In this
Oh, okay.
Okay, any questions with first page? I'm going to skip the bottom half because we just did a bunch of problems with table of values. Let's skip to the back page. Okay, now the top of the back page is the limit definition of area involving summation formulas and all that. I'm going to save this for tomorrow. I want us to do some additional practice with power rule and integrals, and then we'll circle back to number 5 tomorrow. Okay, so let's go to number 6. This is page 12. Let's go to number 6. Number 6 says find the most general antiderivative. We're just going to take the antiderivative of this expression, go through power rule, and then find our answer. So it says find the integral of h of x dx. I'm just going to set this up. I'm not going to do power rule just yet. However, as I write these terms down, I'm just going to try to clean them up as I see them. So 5x to the 4th is set up and ready. There's no adjustment needed because it's set up and ready for power rule. Remember, we have 3 conditions for power rule, right? Radicals have to be converted to rational exponents. Variables has to be moved. If it's in the denominator, we got to force it to the top. And third, if you see parentheses, make sure you expand it all. We can't have any parentheses getting in the way of power rule. Okay. Pi is nothing to adjust there, so we'll go ahead and write that down as well. All right, so no calculus yet. We're just rearranging and getting things set up so power rule can be applied all at once. Okay, what about the third term though? Do we need to adjust the third term? How would we rewrite this so that it's ready for power rule? Good, so there's two things that has to happen, right? The square root of x will turn into x to the 1/2, but it's still out of place. We'll push it to the top. Anytime you want to force a variable or a value between numerator and denominator, you're going to have to change the exponent sign. So this becomes 1/2 x to the negative 1/2. Again, no calculus here. We're just getting it ready so that we can jump into power rule on the next step. Okay, everybody good here? Okay, how about the last term? How would any adjustment needed here? Good. Okay, so the first thing is understanding that when you move that x, the 3 is not going to move. That 3 is going to stay in the denominator. So x to the negative 3 over 3. Okay, the reason I wrote it out this way initially is to kind of show you that this can look still kind of confusing, right? Even though this is ready for power rule, this still looks a little confusing because you're staring at that 3 below. Okay, and if you the only thing in the denominator is a number, where else can I put that to make it easier visually? Yeah, push it in front, not as 3, but as 1/3. Okay, so I want to continue to remind you that a lot of us get thrown off looking at this going, wait, can I do power rule here? You can, it's just, it looks a little strange, so push it out in front. You haven't changed anything, you've just made it easier visually for your power rule. Okay, everything is set up and ready for power rule. Now we can jump into our calculus step. Okay, so 5x to the 4th becomes, okay, we add 1 to the exponent. Good, so whatever exponent you find in your numerator, that number is going to be copied down below. So these numbers will always match. Okay, okay, how about what happens with pi? Good, pi x, right? Pi is not a variable. We don't do pi squared over 2, right? That's not the appropriate power rule. Pi is like a 3 or 5 or 6. It's a constant. It's going to rise up to first degree. Remember, with antiderivative, every variable is going to rise by 1 degree. Okay, let's work with that third term there. 1/2 is going to stay. X to the negative 1/2. We're going to add 1 to the exponent, which is really plus 2 over 2 if you want to match denominator. Negative 1/2 plus 2 over 2 is 1/2. Whatever you put up in the exponent, make sure you copy it down below. Okay. X to the negative 3 becomes x to the negative 2 over negative 2. And then don't forget plus c. Okay. As soon as you apply power rule, your integral and your dx notation drops out. In place of it, plus c. All right, we have our answer, but we're going to try to do a little bit more cleanup here. So the 5s can cancel out. I'm going to flip that 1/2 to the top. It's living in the denominator right now. If I flip that 1/2 to the top, it becomes 2. 2 times 1/2 is just 1. So they're going to cancel each other out. Just x to the 1/2. Next term, I can multiply the 2 and negative 3 together because they're both in the denominator. But I prefer that our answer has no negative exponents in it. So we're going to push that x to the negative 2 back down to the denominator. It'll share the same space as that 6. Okay, last thing I want to do is number 7 here. This is asking for you to find the integral. Now, you're going to be, we do have integral rules for trig, but I want you guys to be able to grab it from your derivative rules. Okay, so your derivative rules is going to be from first semester. Okay, so if you think about first semester, okay, we'll pick this up tomorrow. Okay. Okay, help session this afternoon. Have a great day, guys. Thank you.